We have already dealt with conservation of momentum during collisions and explosions. Net force equals change in momentum over change in time. All of those things, but we have yet to define the different types of collisions. We have different types of collisions as given in the text you are assigned to read today. So please tell me the name of one of the collisions from the text. Rickard.
Elastic.
Elastic is the name of one of the collisions. You can have an elastic collision. What is another type of collision from today's report today? Cindy. Inelastic. Notice the subtle distinction here. We have one that is inelastic and one that is elastic. You have to be careful to enunciate here because you can talk about something during an inelastic collision or during an inelastic collision. So you have to be careful to get the distinction there. Now I am going to put the word perfectly in front of inelastic. And I'll talk about why the word perfectly is in front of inelastic in just a little bit. So what we're going to talk about is the difference between an elastic collision and a perfectly inelastic collision. So what happens during one or the other? What happens during either an elastic collision or a perfectly inelastic collision? Physically, what happens to the objects? Rick?
Well, in an elastic collision, like the things like after you crash, you just bounce back.
During an elastic collision, the two objects are going to run into one another and then bounce off of one another. So my one-word description of an elastic collision is the two objects are going to bounce off one another. What, Huja, is the opposite of bounce? Right, not bounce is not what I'm going to write, however. What is not bounce? Juliana?
It's motionless.
A one-word description of not bounce. Asher?
Stick.
Stick. The two objects are going to stick together. So the one-word definition I'm going to use for a perfectly inelastic collision is that the two objects are going to stick together. During these collisions, we need to identify whether momentum is conserved and whether kinetic energy is conserved. So the first question, is momentum conserved during an elastic collision where the two objects run into one another and bounce off of one another? Adam.
What was the question again?
Is momentum conserved during an elastic collision where the two objects bounce off of one another?
No.
No. How do you know that?
Actually, yes.
Actually, yes. How do you know that?
Because it's a collision.
Remember, momentum is conserved during all collisions and explosions. So it doesn't matter what type of collision. The answer is yes, simply because it is a collision. Now, the question is then, the difference comes down to kinetic energy. So, kinetic energy is conserved during one of these collisions and it is not conserved during the other type of collision. James, during which of the two collisions is kinetic energy not conserved? During the perfectly, you gotta make sure to put the word perfectly in front of there. During the perfectly inelastic collision, you are correct. When the two objects run into one another and stick together, kinetic energy is not conserved. I, of course, wrote it down. But kinetic energy is not conserved during that. And it is conserved during an elastic collision. Okay, now, why is it that during a perfectly inelastic collision, the two objects, why is it that kinetic energy is not conserved? What is it that happens during this that causes kinetic energy to not be conserved? Learn.
Well, they stop. I mean,
No, during a perfectly inelastic collision, that doesn't mean that the objects are going to stop.
Sorry, cancel each other out because they're I guess,
it doesn't have to do with canceling one another out, because this kinetic energy has to go somewhere. It just doesn't disappear. So where does this kinetic energy go? Go.
Friction.
Friction. I'm not sure what you mean by that. That's a one-word answer.
When the two objects meet.
Yes.
Like during perfectly inelastic collision.
There's friction during an elastic collision, too. Yeah.
Like sound.
Sound is one. Standard. Heat. You could also sometimes have light. This is caused by the deformation of the objects. When you have a perfectly inelastic collision, the two objects run into one another and stick together. In order for that to occur, the two objects are deformed. And you have internal energy in the objects. Anytime you deform an object, you have internal energy. And so you're going to increase the internal energy during that deformation of the object. Now, I have two different spheres. They're called happy and sad spheres. You can decide which one's which. To discuss the different types of collisions. Here we go. We'll start with this one. Hunter, what kind of collision do you think this one is?
Elastic.
It's elastic. Why do you say it is an elastic collision?
Does it bounce?
Because it bounces. Clearly, we have a bounce. Who could tell me why this is not an elastic collision? I agree, it does bounce. Why is it not an elastic collision? Sandra? Say again? There's sound. Number one, you can hear it, right? Which means, class, is kinetic energy conserved during that? No. So one, you can hear it. What else? Doyle?
It's not bouncing back to its full height, like
You
the
could-
original height.
You can also see that kinetic energy is not conserved because it doesn't bounce back to its original height. If it starts here, it should bounce all the way back up to where it started, right? It starts with all gravitational potential energy. It comes down. It strikes. If kinetic energy is conserved, it's going to leave the ground with the same amount of kinetic energy and is going to come all the way back up to where it started. But it doesn't do that, right? So some of this kinetic energy is converted to heat and sound. Okay. That means this is not an elastic collision. This also means it's not a perfectly inelastic collision because the two objects don't stick together. This is what is called an inelastic collision. It's somewhere in between. On one end, you have the elastic collision, which is an ideal case. And the perfectly inelastic collision is on the other side. And in the middle, we have the inelastic collision, which is what this one is right here. Which is why I have perfectly in parentheses there. Okay, what about this one? Goolsby, what kind of collision is that?
Elastic.
Okay. So it bounces, right?
Yeah.
But is kinetic energy conserved?
No.
No. So what kind of collision is this?
Inelastic.
This is an inelastic collision. Again, it's an inelastic collision, right in between, right? It bounces, but kinetic energy is not conserved. It turns out that a lot of, actually most collisions are actually inelastic. They're not the ideal cases of perfectly inelastic or elastic. It turns out that this one simply has more kinetic energy converted to heat and sound. So, and you can actually hear that difference if you listen to this one versus this one. That one is louder because more energy is converted from kinetic energy into heat and sound. All right, so that's just identifying the two different types of collisions. I suppose that we should take a moment to do this. If we do have a perfectly inelastic collision, remember that would be the sum of the initial momentums equals the sum of the final momentums. We've actually already dealt with a perfectly inelastic collision. You did that in your lab, where we had, let's see, the mass of the yellow multiplied by the velocity of the yellow initial plus the mass of the blue times the velocity of the blue initial equals the mass of the yellow times the velocity final of the yellow plus the mass of the blue times the velocity of the blue final. And what happened here was the two final velocities were the same, so you can take the mass of the yellow plus the mass of the blue times the final velocity. So during a perfectly inelastic collision, this is what you get. But we've already dealt with it.